All right, great. Thanks, Alden. Okay, so everyone, sorry for the slight delay. Thank you for joining. So this is part of our data science initiative series on decoding pandemic data. And we are really fortunate to have with us today Evan Ray. Evan is on the faculty at the University of Massachusetts at Amherst. He's working in the lab of Nick Reich, who many of us may be familiar with as the leader of the group that's put together the COVID-19 Forecast Hub. Nick has been deeply involved in those, Evan has been deeply involved in those efforts and is here today to sort of discuss how this came about and how it's being used, and then we'll have a chance to ask questions. So Evan, thanks again so much for taking the time. I know that you know, things with COVID remain really busy, and peeling off even an hour can be difficult. So really appreciate your taking the time to share this with us. And welcome to Brown virtually.
Thank you. Yeah, thanks for the introduction. So what I really think of what I'm going to be talking about today is a giant collaborative effort involving people from institutions, you know, over 50 different institutions in academia, government, and industry. And I feel like, you know, although I've been very involved in making this go, I also feel like I'm just a representative of this very large group of people. So yeah, as Joe was saying, the goal of the Forecast Hub is to collect, aggregate, and make public these forecasts of what's going to happen with COVID in the short term over the next few weeks. And the goal of doing this is to have this as a resource available for people making decisions where they might be helpful. So I wanted to start off by just acknowledging just this very large list of people. There's a lot of names on this screen, and the last item on it involves hundreds more people. So this is just a very large group. I couldn't possibly talk about all of them, but I wanted to highlight Nick Reich, as Joe was mentioning, has been central to this effort, along with Mike Johansson at CDC. But really everyone here has been making critical contributions to this. So I wanted to start off with just a demonstration of a visualization of these forecasts. This is the link that I'll be going to, but I'm just going to switch over to my browser to show you and talk through these forecasts. So can you see my browser screen right now?
Yes.
Great, thank you. So what we're looking at is forecasts of incident deaths per week. So how many people died each week and were reported as having died due to some, basically due to COVID-19. So the gray line on the left is observed data. And then at the end, we have forecasts for what will happen in each of the next 4 weeks from a bunch of different teams and models. And so what we're looking at here are point forecasts, point predictions for what the number of incident deaths in the US will be over 1, 2, 3, and 4 weeks ahead. But we also collect 11 different prediction intervals from each group. So we can look here at the 50% intervals or the 95% intervals from each of these models. So this is one of the contributions of the Hub, just this system for collecting these forecasts from these different groups and putting them together and making them available to anyone who wants to look at them. But this is a lot to try to take in and a lot to try to understand. So another product of this group is the Ensemble Forecast that we produce each week that basically tries to summarize what all these different models are saying and produce a coherent story out of them. So one of the benefits of building this ensemble is just to make this system and the results of it more intelligible to someone who wants to use this as an input to decision making. And another benefit is that it's been shown through repeated studies with different disease systems over the last 10 to 15 years that ensemble forecasts are generally more reliable than the individual model forecasts. So we do this, I've been talking about this so far for the US and incident deaths, but we're also doing this at the level of states and territories. So we can look at the forecasts for Texas. And also for cumulative deaths, so not the number of new deaths each week, but the total number of deaths reported as of a certain date, and for incident cases. And not displayed here, but also collected our forecasts for hospitalizations. So I'm going to switch back over to slides. So I guess what we do is collect these forecasts and make them available. Why do we do it? Well, there are a number of different decisions that public health planners might make that could be informed by forecasts. So one example is a question, do we have enough hospital beds in a certain area? Or if we're gonna see more cases and potentially hospitalizations over the next few weeks, do I need to think about planning for increased capacity? If I have a limited supply of personal protective equipment, maybe I want to look and see where are the places in the near future where it's most important to send those resources. Or if I'm planning a vaccine clinical trial, maybe I want to select sites in places where there'll be enough people to recruit into the trials and follow. So we are not, as the hub, actively engaged in these applications of forecasting, but we are engaged in collecting them. So I think of our contributions as falling in these 4 areas. So first, just the infrastructure for collecting the forecasts. So we have a standard CSV format for representing forecasts, and each week teams submit them by putting in a pull request to a GitHub repository. And there's some automated validations that are put in place just to make sure that the submissions are formatted correctly and satisfy some basic checks for being reasonable, like you can't predict negative cumulative deaths, and your forecasts of deaths have to be, less than the population size of a certain area. So we've got this infrastructure piece, and then some modeling that are products of the hub itself. So the first is that ensemble model that I was talking about a minute ago, as well as a baseline model, which we think of as not intended to be a good forecaster, but just a naive reference model. So any good forecaster should certainly be better than this baseline. And these modeling efforts are where my research time in the hub has gone most over the last 6 months or so. We've got that interactive visualization tool that I demonstrated a minute ago. And we've started to do some evaluation to sort of think about these forecasts and whether they're reliable, whether they give us information that we can trust, and to answer the question of whether some of these models are better than others. So I have done some of this evaluation work, but most of that has been done by a few other people in the group. So I'm going to talk a little bit about those results later, and I'll just be borrowing figures and results from them. So over the next few minutes, I want to talk a little bit about the modeling efforts where most of my time has gone, starting with Ensemble, and then a little bit about the baseline model, and then think about evaluations a little. So I think about building an ensemble. I want to have 2 views of this. And here's the first picture to go with this. The idea is that I have forecasts from all these different models. I have here an example from pretty early on in the 2nd week of June, where I just have 8 models that I'm thinking about for the state of Alabama. And so I've got these 8 different predictive distributions for what will happen in the next 4 weeks, and I want to put them together in a reasonable way. And my mental intuition about what's desirable for an ensemble is that it should be somewhere in between what these individual component models say. And I think about this sort of in terms of a center and spread or location scale sort of way of thinking about it. So if you focus on the 3rd column here of the component models, we've got this forecast from Iowa State, which has very narrow predictive intervals. So they're expressing a lot of confidence about what's going to happen over the next few weeks. And I would argue maybe too much confidence. So maybe those prediction intervals are actually a little bit narrower than is warranted. And on the other hand, the SWC model has very wide prediction intervals, and 4 weeks ahead, they basically say, I don't know, there's like a 2000, there's a range of values for possible deaths that's like 2000 wide. And so maybe we can do better than that. Maybe someone who would want to use these forecasts as an input to decision-making would like a little bit more precision about what's going to happen. So the ensemble in terms of width sits right in between those extremes. It's a little harder to see, but that same idea holds for the center. So the predictive median for the ensemble is in between the predictive medians from these component models. So in a little bit more mathematical detail, we have a bunch of spatial units, which are going to be indexed by S, time points when we're making a prediction, T, and a forecast horizon, H, which is like 1, 2, 3, or 4 weeks ahead. And at each of those combinations, the spatial unit, time point, and forecast horizon, we ask teams to submit 23 different quantiles of their predictive distribution. And those basically define a predictive median, as well as the limits of all the 11 different prediction intervals. So we're going to have notation here that is Q is a predictive quantile from model M, and then the spatial unit, time point, and predictive horizon, and then K will run from 1 to 23, indexing predictive quantiles. And so what we're going to do with these is that at each quantile level, we're going to form an ensemble forecast that somehow combines the forecasts from these different models. So I'll have some sort of combination function F that I'll describe some options on the next slide that takes the predictive quantiles from my M different models and puts them together to give me a predictive quantile for the ensemble. So this is view 1 of building the ensemble. And for view 2, I want to think about, rather than this sort of representation of a prediction, I want to think about a predictive CDF. So this sort of fan corresponds to one view of a predictive distribution. I could take that distribution and look at a CDF for it as well. So here's one example of this. This is for California in mid-July for 1 week ahead forecasts. So what I've done is taken each of the predictive quantiles and matched it up with the corresponding probability level. And that gives me 23 different points for the 23 different predictive quantiles. And if I draw a line between those points for a single model, I get an approximation to that predictive CDF. And so if you focus in on one quantile level, so the last one we asked for was the quantile level at probability 0.99. So that defines kind of the upper end of these representations of CDFs. At that quantile level, my ensemble is going to be some combination of the predictions from these individual models. And we've explored kind of 3 ideas here, basically. The thing we started off with was a mean. So at each quantile level, I'll just take the average of the predictions from all these different models. That's what we started off with for the first few months of this challenge. And basically what we saw was that the mean is sensitive to outliers, and that was affecting forecast skill. So in this example, you can see that most of the models that were submitted basically agree with each other, and they fall in this kind of range over here. And then there's one model that just doesn't look like the others, and it has extremely wide predictive distribution. And especially in the upper tail, that's affecting the mean a lot. It's pulling this upper tail of the quant mean ensemble up. And that was basically not desirable. So we switched in late July to using a median instead, just because that median is more robust to that outlying forecast. And so that median sits more in a representative place of what these different forecasts are saying. And we've also thought a lot about different options for how we could try to use past history of forecast skill from these individual models to say how much weight they should get. And so all of these different variations that we've thought about have been, or most of them, not all, have been some kind of a linear combination. So I'm going to have some coefficients beta, and those are parameters that I'll estimate, and beta superscript m will be small if I don't trust model m very much. So we've looked at these, and I'll basically show you some results in a couple of slides that say this can help, and it can help relative to the mean, but there's not much evidence that it's better than this median idea. So we've stuck with this simpler idea. But you can see here that the reason that it helps and it lines up with the median is basically that it has learned from the history to give low weight to this forecaster. And so it's discounting that forecaster when it computes the ensemble forecast. All right, so that's the second view of the ensemble. And I'm gonna move on, briefly talk about this baseline model. the idea here, the basic idea was suggested by Ryan Tibshirani. But the idea is that we're going to think about forecasting incidence as our main goal, and then we'll get to a forecast distribution for cumulative deaths later. And the way that we're going to forecast incident deaths is by focusing on, well, I guess if I think about the point prediction, the predictive median, I'm going to say that's going to be constant going forward over the next few weeks. And it will be equal to the most recent observed value for incident deaths. And then I'll get a reasonable distribution around that by thinking about the differences in incident deaths week to week over the past of the time series. So I'll say, you know, my point prediction is that incident deaths will be constant going forward, and how much might it change by a similar amount that we've seen over the past. And then I get from this prediction of distribution for incident deaths to predictions for cumulative deaths. If incidence was constant here, that corresponds to a constant slope for cumulative deaths. So there's more to say about that, but I'm going to skip this slide and we can come back to it if there's interest. I'm going to turn to talking a little bit about evaluations. So I want to focus first on thinking about how these different ensemble approaches that I talked about relate to each other. And the evaluation metric that we're thinking about is a weighted interval score. And this is a proper scoring rule for predictive distributions. And you can think of it intuitively as a measure of the distance of the predictive distribution from the observed response. And it can be written, there's a formula that I didn't put here, but basically the formula for it is there's a part of it that's the mean absolute error. And then there's a part of it for each predictive interval that is basically 0 if that interval contained the eventually observed outcome and has some penalty if it missed. And the penalty corresponds to the size of that predictive interval. So a smaller weighted interval score is better because that would correspond to a smaller absolute error and fewer penalties for missed forecasts. So that weighted interval score, or the average of that across many forecasts, is what's on the vertical axis here. So a better method will be towards the bottom of these plots. We've got facets for forecasts 1, 2, 3, and 4 weeks ahead. And we're looking at a comparison of these 3 ensemble approaches and a baseline forecaster. So the first observation here is that at all 4 horizons, the baseline forecaster is not as good as the 3 ensemble methods, or maybe I should think of that as the ensemble methods are doing better than the baseline method here. Looking in a little bit more detail, if you pick sort of the quant median and compare it to the quant mean, so compare the green to the blue, you can see that a lot of the time they are essentially equivalent in performance. And then there are these little times where the median does a little bit better than the mean. So I guess there isn't always a gain from using the median, but there are these times where there was some outlying forecaster that affected the mean and the median does better in those weeks. And the similar kind of relationship holds for the trained ensemble, although it doesn't line up exactly. A lot of the time they're similar. And then there are these moments where the trained ensemble is a bit better. That doesn't hold every week. There are these moments where the trained ensemble is not as good, but in general, that's the story. But if you look at the median and trained approaches, neither one of them is consistently better than the other. So there are times like here where the median is better than the trained approach, and other times where the trained approach is better than the median. Oh, and I guess I want to acknowledge this figure is due to our collaborator, Logan Brooks at Carnegie Mellon. So now thinking about the ensemble approaches as compared to the different component models, this figure is due to Nick Reich. What we're looking at here is, again, a facet for each of the different 4 horizons. Vertical axis is, again, average weighted interval score across different forecasts that were made. And the reference line here is the performance of the baseline model. So that's here. And so the reference line is a little different in each plot and matches up to that baseline model. So methods to the left, roughly, are methods that are doing worse than the baseline model. So there are a few submissions to the hub that are consistently worse than the baseline method. And approaches to the right are better. And you'll see that over here, the ensemble method is essentially the best method out of anything that's in the hub. But the differences between the ensemble and the best component models are generally quite small. So this model by Yu-Yang Gu, who's like an independent data scientist, is very good. And then there's a model produced by other people in our group at UMass, but not, you know, a product of the hub, that also has done quite well. I think I'll also not talk in depth about this slide, but weighted interval score was composed of these parts having to do with mean absolute error and sort of penalties for missed predictions intervals. So here, let's just look at mean absolute error, and the ensemble again has best mean absolute error. And we again see that there's a collection of models that are actually worse than the baseline. What's interesting here maybe is that for 1 week ahead forecasts, the baseline is actually best on average. So it's really at the larger horizons where we see that there's more to say from these models, or they offer more benefits. I'll skip probabilistic calibration for now too, I think, but happy to come back to it. Basically, the calibration is not bad. And I wanted to highlight a challenge. So, you know, the effort has been largely successful, but it hasn't been perfect. So a challenge that we're facing right now is that over the last 5 or 6 weeks, cases have actually been rising. And so, and that has not been captured by most of the models in this system, and therefore it has also not been captured by the ensemble. So this is heading into mid-September. We had seen a decline for a while, and most of the models in the system predicted that that decline would basically continue, with a couple of exceptions. So, and, you know, maybe that's reasonable, but I think also there was a lot of human speculation that maybe as schools were starting up, people would start to become infected again at higher rates. And that's what we've seen. So I guess there is maybe some human intuition that was not picked up by these models and has continued to not really be picked up very well. So I think in general, the forecasts for deaths have been better than the forecasts for cases. So there's a lot of ongoing work in this effort. We've got this weekly process of just taking in these forecasts and processing them. There are some challenges to doing this that we're still working on. We've got a very large amount of forecast data. I think the GitHub repository with all of these forecasts in it is something like 15 gigabytes now. So we're thinking about how to store these forecasts and make them accessible in a robust way. And something has also come up where teams occasionally realize that they had a bug, and so they need to kind of fix their forecasts. And in terms of, I guess there's sort of a tension here about, do we want to allow them to change their forecasts? An advantage is that if we do allow them to revise a past forecast, then that'll be more representative of how their model was actually doing as it was intended to work. And maybe that could help train an ensemble, for example. But that also sort of messes with the scientific validity of the experiment, where a forecast is made before the observed outcome occurs. So a solution to this is maybe to keep track of versions of forecasts so that we have the original submission and also the fixed submission. There's more exploration ongoing into thinking about the ensemble methods. So some recent idea has been to think about a weighted median and see if maybe that's helpful. There's maybe not strong evidence yet that that's helpful, but it's a possible direction. And I think the real challenges to ensemble methods are mainly that the models change over time. So people are constantly tweaking their models. And that means that how good a model was 2 weeks ago may not be very representative of how it will be this week or next week. So using past history to train the ensemble has proven challenging in this setting. And then there's a lot of, I guess, I'm interested in going back to doing actual development of forecasting models. So in flu forecasting, which is what we've been doing with CDC over the last several years, as well as in the similar COVID forecasting exercises happening in the UK and in Germany and Poland. It's been seen that some sort of standard time series models are really effective at forecasting and are often better than the mechanistic epidemiologically derived forecasting models that are used by most of the people in this hub. So I guess that's what I've been working on with my extra time over the last maybe month or so, thinking about specifying some more standard time series models. So with that, I want to pause the part where I am talking. Once again, acknowledge all the work that's gone into this from all these different people. And I want to advertise that we are hiring for a postdoctoral position. So if you or anyone you know is interested, you should get in touch with me or Nick.
Okay, thank you, Evan. I was just having a little bit of trouble with the mute function there. This is really an extraordinary collaboration. It's really, and I know you've only sort of given us the thumbnail sketch of it. It's hard to imagine how much work has happened behind the scenes. So, so right now we have there was one question that was submitted while you were speaking, so I'll go with that question first. And I've actually written down a bunch more. I'm sure we won't get to all of them. And so I would say that for those who are on the Zoom link, that you can either send your question into the chat, or you can use the raise hand function, and we'll just have you ask your question out loud. And if you do want to ask your question out loud, I would just ask you to turn your camera on and say who you are and where you're from. So, so the first question we have came from Tom Tricklinos, who's a professor here at Brown in Health Services Practice and Policy. And Tom has been really leading the way for a lot of state level modeling here in Rhode Island. And so his question is, and I hope I'll ask this correctly, but he says, can you send predictions? I think he means, can people from the state send predictions from a state specific model, or are you only using models from groups that are doing US wide kind of predictions? So I guess that these models that you're using the modeling groups are doing models at the state level, but I don't know if you're getting specific inputs from states themselves.
Yeah, so you can definitely submit for a subset of the locations. And so this is a plot of, this is a couple months old now, I think, but this is a plot representing forecasts. I don't know, so location is on the horizontal axis, and we've got a collection of models on the vertical axis. And the color here is indicating, you know, which models were available and passed some basic criteria for inclusion in the ensemble. And so definitely there are teams that have submitted for just a small number of locations. For a while, there was a team from Illinois, from Chicago, who was submitting basically only for Illinois. So that's certainly possible. And if I could riff on the question, there's like a statistical question that comes out of this, right? Which is how to deal with the missing forecasts when you are building an ensemble. And basically the idea, if I can find a slide here. Yeah, too many slides, okay. The idea has been basically a imputation followed by redistribution of weight. So suppose that you have a location where there are 3 models, but one of them has a missing forecast for that location. So the idea is that we're gonna use a mean imputation to fill in the missing quantiles for that model as an average of quantiles from the other models. And that means that I have a number to fill in for that model's forecast in that location during optimization and training of ensemble weights. And that means that a part of the weight that's assigned to that team during training really belongs to the other models that were used to impute its missing forecasts. And so you can sort of break down the final forecast by sort of substituting in the forecasts from the other component models, and think about what was the effective weight given to each model during training. And so this results, you sort of do mean imputation to fill in missing data, and then some of that weight actually belongs to other models, and you redistribute it to those other models when you're making a forecast in real time. So this, the other strategy that we thought about for dealing with missing forecasts was to partition the locations into different groups of locations where the same set of models was available, and do estimations separately for each of those locations, so that we would have like a complete data. But the mean imputation had definite noticeable gains in performance of the resulting ensemble. Yeah.
Right. Okay.
So I think I'll wrap up. Yep.
No, that's great. I think that's really good information to have. Let me just pause for a moment and see if anybody who's in the audience would like to ask a question. I haven't seen the hand raised, so I'll just pause for a minute and see if anybody wants to jump in. So seeing a question from Huang Chu, who's here in Rhode Island, and let's see. So Huang,
Hi,
I'm looking
everyone.
for you. Okay, Huang, go ahead. I think you're unmuted.
Thank you so much, Joseph. Thank you, Evan. I think the work is really, really great, and I personally, currently, I'm doing some analysis for the policies as well to see the impact of the policy in Rhode Island. But related to the work, I have some questions that I want to ask you. It seems like we're using some data science method into these models. I want to ask you if you can talk more about the predictions that they have been using for these models, like are they using like mostly based on the demographics variables or COVID symptoms or policy? Because I feel like these today, I feel like I want to hear more about like how the policy impacts to the COVID-19 so far. And based on these slides, I haven't have a sense of how the policy apply here in this model. So it would be great if you can give me more information about that. Thank you.
So Huang, if I could just ask you, are you asking how the models are used to evaluate the effect of policy, or how policy is used in the prediction, or maybe both?
Yeah, maybe both. So I just don't know, like we talk about like using a set of predictions here, but I'm not so sure like which predictions are we talking about. And like, I'm just curious about that. And, you know, when we run offline machine learning in this concept, it will be like a lot of variables for prediction. So I just don't know, among all these models, is there any models that you have been, that they have been using policies at the predictor or not?
It's a good question. So there's so many groups participating that I think it's like almost every modeling strategy has been tried and is represented among these groups. Let's try to get back to one of these pictures. I just want to try to run through some of these models and what they do as maybe a way to answer this question. So the Umass model, which I may be most familiar with, has the so the Umass model has a structure that's a compartmental mechanistic model, and it has a structure where it would allow the rate of transmission to depend on covariates. And so an idea is to plug in covariates like what is some policy that's in place, like is mask use guidance in place in this location. And so that could potentially inform forecasts. That group has looked at doing that and basically found that did not contribute to forecast skill. So they've looked at that as sort of a way to do inference, but I don't think that those sort of policy effects are in place in the actual generation of forecasts that they submit on a weekly basis. There are some of these models, like the one from Carnegie Mellon, that just outright is a time series model and has no room for thinking about policy in it. And then there are a couple of other groups, like the one, or there's a few groups from Johns Hopkins, but one of the groups from Johns Hopkins, as well as a group from Columbia, have models that were really designed as models for evaluating policy. And so they have very complicated systems built in for thinking about policies that are in effect in different locations at different points in times, and that those are used to inform their forecasts. I think an interesting question is whether those, whether including policies is helpful for forecasting. And I think the answer is not totally clear. Like UMass has its answer that it wasn't helpful for their particular model, but I could easily imagine there might be other model structures where incorporating forecasts or incorporating policy into forecasts would be helpful. And I think just going back to this challenge that we're facing of, you know, this situation with the case forecasts being sort of bad. It seems to me that there's room here for incorporating something more informative in a lot of these models. Like, why did a human look at this and say things might start increasing again in September? It's because we knew that people would be getting together in situations like schools, and that might lead to more transmission. And so I think most of these models don't have a great way to capture that right now. And many of them are exploring it and might benefit from it, is my opinion. But I guess that's not a formally known thing.
Thank you so much. I think that is really a great answer, because like if we see that a lot of cases gonna increase in the future, maybe we would look at that time and maybe we want to apply more policy during that time to reduce the cases. Thank you so much.
Thank you, Huang. I'll
Joe,
pause again to see if there are any other audience members.
Can you hear me?
Yes, yes.
Hi. That was a wonderful talk, Evan. And what I would like to ask is, can you tell us a few more things about the WIS, the weighted interval score? I mean, is it a proper score in the sense of, you know, be encouraging people to be honest in the way that they describe? I mean, usually, you know, proper scores are like the logarithmic score or other variants. I haven't seen that before.
Yep, it's a proper score. So here's just a slide about the weighted interval score. So as I indicated, so I guess it's, let's see how to break this down. I almost want to talk about it backwards. The score is a proper score. So this means that, let's see if I can summarize the definition of a proper score. It basically means that in expectation, the true data generating process would minimize this score. More intuitively, what that means is that a forecaster doesn't have any incentive to report anything other than their true beliefs about what will happen. So the reason that we have used the weighted interval score, so as Thomas mentioned, a logarithmic score or CRPS are some other common proper scores that are more commonly used. And in past forecasting exercises with CDC, like for flu, we've used a log score. But that wasn't really possible with this format of representing forecasts in terms of a predictive median and then predictive intervals, because a log score requires that you know basically the full predictive distribution in order to evaluate the predictive density. That's a digression. So basically the reason we're using a weighted interval score is because it matches the data that, or like the representation of forecasts that we have available. And the way that it's constructed is that if you think about one predictive interval, the score is going to have contributions from the width of the interval and then basically a penalty that, so here's an indicator function that says that the observed outcome is less than the lower bound of your predictive interval. So a penalty if the interval is too high, and an equivalent penalty if the interval is too low. And the size of that penalty is like how badly did you miss, the difference between the lower bound of your interval and y. So a smaller interval score is better, and a weighted interval score is a combination of interval scores across all of your different levels of predictive intervals. So this is, it is a proper score. It's been less commonly used for epidemiological forecasting, but it has been used before in a variety of different forecast challenges, including I can't quite remember now, there's like an M3 challenge, I think, that used this, and a few other challenges based in Europe mainly. But there's a preprint about this here that describes it a little bit more, talks about it more if you're interested.
Thank you very much. I just downloaded the paper. Thanks for this. Wow,
Yep.
There's papers written, Joe, about things we don't know.
Yeah. I assume somebody's written a paper about something we don't know. Okay, I'll pause again, see if anybody else from the audience wants to jump in. Okay, I wrote a half a page of questions here, Evan, but I'll try and pick one.
Okay.
Maybe a generic sort of question. I think you partially answered this. So just zooming out a little bit, what you're doing, I think, is you're just going to people and saying, give us your best prediction, and I don't really care how you got it. Does that sound about right? Or do these models, like, because I think there's been a lot of discussion about how to do models. Like, do we write down a mechanistic model like SIR? I think a lot of folks have done that sort of thing. That's been sort of the go-to approach, and then generate predictions. I've seen a couple of places where they're just sort of extrapolating time series of observed data without an underlying SIR model. Do you care about this, or like, how do you, what kind of models go into this? And are you, there's no mechanistic model underlying what you're doing, I think, but you're taking a variety of predictions basically based on different kinds of models.
That's right. Yeah. So we don't care. We don't have any restriction on what kind of specification someone uses. The only restriction are that they're able to generate a properly formatted forecast file. So there are teams using mechanistic models. I'd say that's probably 3/4 of the groups are using these mechanistic models in some form. And then there are teams using just time series models. On the list of performant methods in this challenge, the top 2, at least, probably more like the top 5, are all mechanistic models. But also the worst ones are mechanistic models. And I think actually on this slide, the top 2 are mechanistic models, but then I think the third one down was GT deep COVID, which is like a neural network method. So we don't have any restriction. We'll take any forecasting method. And what's been sort of amazing to me is that you just put them together with a median, and like it works out. It's sort of magical, but it has.
Yeah. I mean, so that's fascinating. I mean, I suspect by doing this, there's an incredible amount of knowledge to be gained about sort of the relative merits of mechanistic versus empirical modeling. I don't know if you've thought about, summarizing, maybe having a synthesis paper about this or something, but it just seems like a tremendous amount of information is in here about how these things work. Information that maybe we were not able to glean previously because mechanistic models or empirical models are just being applied sort of to smaller scale problems. And, there's always been sort of a back and forth between like statisticians and modelers, like the merits of each approach. And I feel like not that we'll ever resolve that fully, but we have a lot of information about that now. It's almost like a natural experiment about models. So I don't know if you guys have a chance to catch your breath and think about that, or any sort of pearls of wisdom you can drop on us about this.
I guess there are two people in our group who have thought about this. It's been something that I personally have thought about a little bit less. I think my personal view is that you can get good forecasts out of both mechanistic and general time series modeling frameworks. And that, this is sort of a cheap answer, but like what's important about developing a forecasting model is that you're careful, that you validate what you're doing, that you look at plots of the forecasts, see where you're going wrong and make adjustments. So like, it's almost like the process of forecasting and like building your model carefully to match the data is, to me, what's most important. And I guess there are compartmental models that do a terrible job of forecasting and compartmental models that do a great job of forecasting. And to me, what separates those is not whether it was a compartmental model or not, but like how careful were the people building that model. And it looks like, the top two approaches are pretty much mechanistic models, but number 3 down here is not a whole lot worse, and that's a neural network approach that has nothing mechanistic in it at all. Some of the people who have been thinking about this more than I may have teased out more of a careful statement, but that's just my take on it.
Yeah, okay, that's really helpful. I mean, it's sort of, it says we should be scientists when we're doing our modeling, I guess, is what it comes down to, no matter which method we're reaching for. Let me ask a bit of a provocative question. So this morning in the New York Times, I read a story that says, well, there's people talking about how there's no evidence that schools are sources of outbreaks, or no evidence that schools are, in other words, there's a movement afoot that says, like, we should just be sending the kids back to school, for heaven's sakes. This isn't a big problem. And I think that I'm actually sort of sympathetic to that, because, you don't hear about a lot of super spreader events coming out of schools. But if we look at that plot you kept returning to, it seems pretty clear that when September rolled around, there was a pretty sharp increase in cases. I mean, people could attribute it to COVID fatigue. People are just tired of wearing masks. There's obviously the college students that are in the mix there too. But do you have sort of a take on that? Like, I certainly wouldn't want to be the person running around saying, like, close all the schools, but at the same time, it doesn't seem quite right either to say that opening schools has no impact on the pandemic.
Yeah, I don't have a formal scientifically backed take on this, but it certainly doesn't feel right to me. Just anecdotally, there are so many cases associated with colleges and universities that seems a little bit hard to believe. But I have avoided that controversial part of scientific research.
Okay, good answer. I won't keep you on the hot seat then. I just didn't know if you had a hot take, so to speak, about this. But
so can I break your monopoly on questions?
Please do. I've been hoping for that.
So since we are on this slide, what do we know about the performance of ensemble methods in general? So here we have a situation where the ensemble does better than any of the constituent parts. But and I suspect that depending on the way that you do the aggregation, there must be guarantees that you would have about how worse the ensemble could be with some asymptotic. Apart from the practical thing, do you have any literature that you could suggest? There's a reason why I'm asking. That's quite self-serving.
Okay. So I think this is an interesting question, and I think there are, like a lot of questions, there are simple settings where there's an answer and complicated settings where I don't know of an answer. And I think a simple setting is if you're thinking about point forecasts. And if you think about point forecasts, there is a way to think about ensembles in terms of a bias variance trade-off. And so you can think about if your point forecasters are independent and unbiased, and I just take an average of them, then I will have achieved a variance reduction. And so basically, for point forecasts, the way that I personally think about the reason that ensembles are useful is because of the variance reduction. And there can also be a bias reduction as a potentially smaller effect if you have component models that are biased in opposite directions. Then taking the average can get you a bias that's closer to zero in between. So that's how I think about this. There is some literature about this that I think you could find in Hasty and Tibshirani, the elements of statistical learning, related to justifications for random forests being useful in terms of that variance reduction idea. A setting like this, I think, is less explored because we're thinking about predictive distributions, so the full predictive distribution and evaluation of that. And I guess I have not seen a very sort of deep theoretical justification or explanation of, if you're thinking about predictive distributions, why a log score or weighted interval score would benefit from ensembling in a theoretical way. We have done this for flu over the last several years, and similar studies have been done for dengue and Ebola. And the consistent sort of empirical finding in applied settings is that for infectious disease forecasting, the ensemble in all those cases has been either better than all components or very close to the top of the list, maybe with one or two component models doing better than it.
Thank you. Thank you. We do our own mini ensemble for the state-specific prediction. So we have a family of variants that we do a similar thing.
Have you, in that system, have you explored any weighted ensemble approaches, or has it been some of the simpler things like means?
Yeah, there's a variety of things from a simple average to some approaches that we found buried in the optimization literature based on eigen decompositions of some stuff that you create to simple regressions. And it seems that the average was working, the average or the median is working well. So I just don't know if there's anything known about what you should be doing rather than approaching it empirically.
Yeah, I don't think that there is a general rule or anything. This is the quantile ensembles, similar to what we've been doing, have been explored a bit in the econometrics literature. And I think the result was that it depends a lot, the right approach depends a lot on the specific characteristics of the forecasters you're combining. There's a nice little simple expository paper by Bussetti, I think, about quantile regression averaging, I think. I can try to find that reference, but basically it has some simulation studies and compares approaches similar to what we're doing and density averaging, so like a mixture of the models rather than a quantile average, and a few other strategies. And it basically finds that quantile averaging does well in a lot of settings, but there are other settings like varying bias or varying variance of the component forecasters where the other approaches are better. So I think it is sort of something that you have to look at your specific setting and see what works.
All right, well, I notice we're coming to the top of the hour. Evan, this has been really, really terrific. I'm again glad you came. I think we got to get some insight on some technical aspects, some non-technical aspects. Personally, I'm still just really floored by the scope of the effort, and it's really, really impressive. So congratulations on this. I think we're going to sign off now. Evan, if you wouldn't mind just hanging out for a couple of minutes as we allow folks to leave the seminar and move on to whatever they're doing next. And I'll just say thank you again, and thank you everybody for attending.
Thank you. Happy to be here.